In previous video, we already explained and introduced the so-called D-square law for the droplet evaporation and combustion. And as you understand, for D-square law, basically we assume the droplet and the environment, the ambience are stagnant, and we neglect the influence coming from the flow convection, including the forced convection and the natural convection. Then we understand that this square give us a very nice results to think about the droplet variation in the hot environment of surrounded by a diffusion frame. Basically, the liquid surface, I mean the D square represent the surface area of a spherical droplet is linearly decreased with respect to time. And this is very clear to let you know why this is a so-called D-square characteristic. D-square means the surface area. Actually, when you go back to think about the detail, the flow structures for your diffusion frame or even for the droplet under a pure evaporation, you will realize all the transport mechanism governed by diffusion. Okay, then if you think about diffusion, as we mentioned earlier, the diffusion transport basically is a so-called is a surface characteristics. Okay, because all the diffusion transport will go through surface lines. Okay, there is a surface. The units for the diffusion coefficient is the meter square. That means that there is the area change characteristics. But now we understand based on the D-square law, the droplet evaporation or combustion mainly controlled by diffusion process. But we are thinking about how the influence coming from the flow convection. You try to think about a droplet moving in the gaseous stream, or maybe the gas had some flow, and those flow will interact with the moving droplet, and based on their relative velocities, then droplet will experience the flow acting on droplet, okay, even acting on the frame. And if you think about another factor coming from the natural buoyancy, that means that if you consider gravity, because when you burn the droplet, you always experience the influence coming from the gravity. Then if you have a flame, that means that you will have a density difference on the droplet flame. Then the buoyancy effect, the natural convection comes and acting on the droplet and the flame. Then we try to think about how to describe the influence coming from those flow convection, include forced convection and the natural convection. Look at these figures from the figure A, B, C, D. We try to give you some comparison. Originally, you understand for figure A is the purely evaporation conditions. As an environment, we do not have oxygen, or maybe the temperature is low, is lower than ignition temperature, then your diffusion flame cannot be generated. In this situation, then we are thinking about the droplet is purely under evaporation process. But when the temperature increase, I mean the ambient temperature try to increase is higher than ignition temperature, definitely the gasified fuel vapor will have a chance to meet with oxygen from the outside, and temperature is good enough for ignition, then you will generate a spherical diffusion flame ideally, because for the case A and B, both of them, for both of them, we do not consider the flow convection. That means that we eliminate all the influence, especially from the gravity and also the flow, and you will have a perfect spherical droplet surrounded by the spherical diffusion flame. And based on these kinds of structures, as described in figure A and the figure B, we can have a D-square law theory. Okay. Now we try to think about now if you we introduce a flow convection into your droplet. Think about it. Without consider the combustion, you will figure out if you have a droplet suspended in a flowing stream. This flowing stream, as we remember from the study on fluid mechanics, when the flowing stream approaching to a droplet, actually they will produce so-called the stagnation point flow here. Okay, and the flowing streams they will move to the side of the droplets, and later they will follow in the downstream side. This is a basically from the figure C. You can see the schematic diagram of the flow configuration for the convective droplet combustion. Okay, here, and you can see flow stream. If you do not see, you assume there is no combustion or initially, you can see the flow stream will be diverse, then move along with the side surface of a droplet, then move to the downstream side. This is basically they tell you the stream lines of your gas particle will move by along these stream lines. Okay, at the same time, you can see because the liquid phase it basically is the free surface. It's not like the blood body. Blood body usually we consider is a rigid body surface. Rigid body surface means a solid surface. Then you will not have a velocity slip. You will not have a velocity slip on the surface. Okay, and here they will produce a big shear stress, as we remember from the flow mechanics. But in this case, since we have a flow flowing through the surface of the liquids, and those motions will initiate the motion of the liquids inside of your droplet. Okay, they will produce the flow motions, the liquid motions inside of the droplet, and with the velocity directions accompanied with the outer flowing gas medium. And here, since we assume this is a symmetric spherical droplet, then you will have a symmetric a couple of the recirculation zone. Here, they tell you this is a very interesting behavior. Later, I will mention here. This tell you this is a very good application for the multi-component droplet. Multi-component droplet means that you mix different kinds of component liquid to form a droplet. Okay, sometimes the mixing is incomplete as from the beginning, but in the combustion process, if you think about if you have a couple of recirculation zone, recirculation means you stir the mixtures inside of the liquid, and they may produce some more good mixing when you go through the combustion process. But anyway, the first interactions with between the gaseous flow and the liquids, you will figure out those kinds of motion coming from the gas phase will be attached to the surface of liquid, then induce the recirculation zone inside of your liquid drop. This is the first one you need to understand the influence coming from the flow convections. But in this case, as you remember, we have a very nice, this is basically the laminar type flow, and they can have a very nice continuous stream lines continuous to the downstream sides. Okay, now you think about for the diffusion flame. Definitely, if the temperature of the flow stream is high enough, they will ignite the diffusion flame. But now the diffusion flame may not maintain the spherical shape. For the droplets, it is still easier to maintain the spherical shape because the surface tension of the liquid is very large, and they can maintain their spherical shape. But for the gas phase, usually, as we remember, for the case B, if the droplet is spherical, then we will have a spherical diffusion flame if you do not consider flow convection. But when you have a flow convection, when you look at the front region of your droplets, actually in this region, from our fluid mechanics study, we understand this is so-called stagnation point flow, then they will face more strong flow convection, and the flow velocity will drop sharply to reach equal to zero at the stagnation point. just in front of the droplets. Okay, in this region, actually, the diffusion flame will push closer to the liquid surface. Okay, this is tell you they will experience a strong convections, and this flow convection will push your position or your diffusion flame closer to your spherical droplet surface. Okay, in compare with the original spherical diffusion flame. And in the downstream side, actually, the distance between the liquid surface and diffusion flame is enlarged. Okay, and this is just like the increased flame length of the diffusion flame. Okay, the tail. Okay, then you can see the spherical diffusion flame will be change their shape. Okay, and they have a smaller separation distance in the upstream side, but longer separation distance in the downstream side. This is a typical spherical droplets in flowing streams, and this flowing stream has a smaller flow convection strength. Now, if you continuously increase the flow strength of your flow streams, what happens? The first one you will see, since from the purely fluid mechanics tell you if you have a very large flow strength, that means higher than certain value on Reynolds number, there is a so-called flow separation occur. When you have a flow separation occur, then you will produce the flow AD in the downstream of your droplet. Okay. Now, when you have a pair of AD, then there is have a pair of AD exists in the liquid side too. Okay, now you can have those kinds of recirculation region, a couple of recirculation regions exist inside of the droplet and also in the downstream of your droplet. Okay. And this is for the flow structures, and you understand when the flow stream is the strength of flow stream becomes stronger, then they will push your diffusion flame as closer as possible to the liquid surface, and then you will see there is a small separation distance between flame and the liquid surface. But the tail is the length of the diffusion flame is increased furthermore. Okay. And this is the shape of a diffusion flame we may have. Okay, up to now we just think about the flow strengths in the gaseous medium are strong enough, but if you continue increase, now you can figure out. In our previous discussion on premise flame, we know when you increase the flows and the flow stretch will increase for the opposite jet flow or stagnation point flow, right? And those flow stretch will give you some suffer for a given control volume without supplying enough reactants into, since that you carry all the reactant out in a short time, they do not have a time to finish chemical reaction. That means the flame cannot exist in this region, okay? Especially in this region, in the upstream region of your droplet. Since the flow convection is very strong, they carry out the fuel vapor and also oxygen to the side, to double the both sides of the liquid droplet. Then this flame, originally located at the stagnation point regions, will disappear. That means extinction. And this is this phenomenon is very similar to the so-called dip off of a diffusion flame, right? Originally, the diffusion flame of a droplet stabilized at the region of the stagnation points, but now they cannot stabilize here. Then they will dip and try to find a possible positions for stabilizing the diffusion flame. Then now you will find out the original envelope diffusion flame will disappear because the former flame diffusion flame disappear, then they will stabilize on the sides of your droplets, and we call this will be the side flame. Okay, you just imagine. Later on, I will give you I will show you some slides, and you can see from the experimental observation. And later on, you continuous increase the flow strength, then the flames will be pushed out to the downstream side. then you will find out those kinds of chemical reaction will exist in the wake regions of your droplets. From our flow mechanics study, when you increase flow strength as much as possible, you find out they will have some kinds of flow vortex exist in the downstream that produce a certain amount of flow eddies in the downstream side, and locally they show you some chemical, some turbulence in behaviors in the downstream of your droplets. And even you can see a so-called Moncarbon vortex. Okay, then those kinds of vortex streets will occur in the downstream side. In this moment, actually, the diffusion burning, a diffusion flame will be pushed to that region, and they do not show the typical nature for purely diffusion flame, because they will get involved with the turbulent mixing. Okay. This is just to give you some idea to look at the influence coming from the flow convection. Simply say that if you have a flow stream coming to meet with droplets, you try to increase the flow strength continuously from small velocity and increase the very large velocity. You will figure out from the beginning your droplet may have a spherical flange. Now, when you experience the influence coming from the flow streams, then the flange will change their shape as oval shape, and they have a small flange distance between the droplet and the diffusion flame, but they have a longer separation between the liquid surface and the diffusion flame. And this behavior will more or more strengthened by the increase in the flow strength. The front flange will closer to the liquid surface more, and finally will be extinction. Then the envelope flame will become the so-called side flame. Side flame means they stabilize at certain regions in the surrounding and without attached to the front regions. And this side flame cannot stabilize too long, then will push to the downstream region, and becomes some kinds of has a turbulence, the diffusion flame, because all the things mixed together based on the turbulent mixings. Now, I try to give you another experiment to let you experience those kinds of variation. Now, we go to the free-falling droplet experiment, and this experiment actually was performed by our research group, and the experiment system is very similar to those kinds of systems reported in the literature. But we find out there's some interesting experimental results, and I want to show you. Okay. Now, in the middle, this is a mechanism for our experimental apparatus. Simply here, there is the two. Number two represent the droplet generator. We generate a string of the droplets, and those droplets are passing through a combustion chamber. B is a quartz combustion chamber, and when they passing through into the combustion chamber, they were passing through a flat flame at first. Okay, and here this is the burner. We supply the premixtures of mixane and to generate the flat flame, and this flat flame is the ignition source for your droplet. Which means when you have a droplet passing through this flat flame, then droplet will start to will be ignited and start to be enveloped by a diffusion flame. And experimental techniques, especially for observation and recording for droplet image, basically we use the same techniques as those presented in the literature. Okay, and here I tell you there's some results. If you use the continuous photoring, then you can have these kinds of pictures. Here, this is a case. I forgot what kinds of fuel what we use, but anyway, you think about it, is the pure substance of a liquid fuel, and we control the environment oxygen concentration equal to 21%. The initial droplet size starting from the before the heading into the combustion chamber, the size is around 500 micron. And we try to change the separation distance between droplets. Okay, since we can control the frequency of the piezoelectric transducers, then those kinds of droplets separation distance will be a change. When you have a smaller separation distance, then you can see the droplet strain is more condensed, and the burning the burning strains is very intense. You can see there is the yellow flame represented is a diffusion burning characteristics even for droplet burning. Okay. Now, if you increase the separation distance from 2.5 to 5, 10, 30, and 100, you will see the luminosity becomes less, which means the burning intensity become less, since we do not have too much droplets exist in the combustion chamber. Since the separation distance increase, therefore, for given control volume, we do not allow too many droplets. They separate over larger distance. Therefore, the yellow color, the luminosity intensity become less. Okay. Before we go to the droplet image by high-speed camera, we need to have some explanation for the generation of a string of the droplets. Okay, this is coming from later on we will introduce it again for the spread, because the spread give you the idea there is a bunch of liquid fuel, right? But you want to break it into the so many tiny droplets. How to do it? Actually, we can use the pressure or use the trim. That means another fluid to have a strong interaction. Then they will produce the droplet or liquid breakup to produce so many droplets. But the original idea coming from if you have a single jet, tiny liquid jet, can we break this tiny liquid jet to many droplets? The idea is coming from the so-called instability of a capillary jet. Okay. Now, usually people from our experience, we find out a liquid jet injecting from a nozzle, I mean the very small droplet, very small diameter of a liquid jet injecting out from nozzle into ambient gas. Ambient gas, maybe you can treat it as a stagnant environment without flow convection. And they tell you from our observation and theoretical prediction, we find out this liquid jet may break up into small droplets, depends on different kinds of disturbance, even very small minutes of disturbance. This disturbance, different kinds of disturbance will give you a chance to break up the liquid jet into the small droplets. Okay. And those disturbances may come from different forms. For example, from the surface displacement. Okay, if you have a flow coming, moving, flowing on the liquid jet, and this kind of disturbance will change the liquid jet surface, and it is possible to break up the liquid jet into droplets. The other one is the velocity or pressure fluctuation in the supply systems on the jet or on the jet surface, and those fluctuations coming from even the liquid properties. Okay, for example, temperature, viscosity, and the surface tension. This is the general comments on the breakup of a liquid jet into the small droplets. Then I tell you how to make this possible in the experiment. Okay, there is because we already mentioned those disturbances may be coming from the surface displacement, pressure, velocity fluctuation, and also the fluctuation in liquid property. Then let's look at how to make these kinds of disturbance. The surface disturbance actually usually be made by different experimental systems report in the literature. Generally, they use a so-called piezoelectric transducers. In previous experimental observation, I tell you they use the piezoelectric transducer attached to the glass tube, and your liquid flowing in the glass tube. Since you have a piezoelectric transducer, they have some. We change the voltage, then they will have some excitations on the liquid fuel inside of the glass tube. By this kinds of periodical pushing, then the liquid inside of the tube will experience contract, expand periodically. Then those kinds of motion on the liquid surface will continuously extend to the liquid jet injecting out, and those kinds of surface variation further continuous, and when the amplitude large to a certain value, they will break up the liquid jet into the small droplet. I will give you the example to see the breakup mechanism. Pressure disturbance is another way. For introducing pressure disturbance, you can do the experiment by applying a sound wave. Sound wave represents is a pressure wave on the liquid jet. Then you can see those liquid surface will be changed by applying the sound wave. Velocity fluctuation, you can start and apply the change your flow rate from the beginning to using an oscillating flow. And a temperature disturbance, you can control a periodical heating on a jet. Okay, and also you can try to change the liquid properties. Okay, for example, the liquid surface tension by change the temperature. Those kinds of techniques were applied to study the instability of a capillary jet in the long history, and you can find it from the literature by yourself. Now I give you the results to tell you those kinds of application of disturbance. They need to reach a certain value, then you can produce a very nice breakup. Okay, these are two examples. Okay, they use the same jet diameter based on water. The figure 1.1 is a water jet with diameter 0.27 millimeter. Velocity is around 3.3 meter per second. The condition is quite similar shown in the figure 1.2. The diameter of the jet is around 0.27 millimeter. They are the same. Velocity is slightly smaller, but it's not too much. It's not too much difference, 2.9 meter per second. Okay, but they apply different frequency, or you can see the wavelengths are different, because when you change the frequency, then you will change the wavelengths occurs on the surface. Okay, in the figure 1.1, the wavelength is longer and is around 11.3. Okay, 11.3. And here they show you those kinds of French shape variation has a possibility to break the liquid jet into the droplet. But actually, this is another good one, because you have a large droplet accompanied with satellites. Sometimes you can even have 2, 3, 4 more satellites, and those kinds of breakout that give you some trouble into the experiment. And those kinds of breakout, actually, they tell you the wavelengths, or we call this frequency, do not match on the breakup, on the natural frequency required for breakup. Later on, I will give you more understanding about the so-called the radar instability, and there is some criterion to match the required frequency or wavelengths to break up the single droplet very nicely. And the result can be found from the figure 1.2. They tell you if the disturbance is smaller, then actually they tell you, they show you the wavelength ratio to the diameter ratio in figure 1.1 is 11.3. But for the figure 1.2, they show you just a smaller one, 4.6. At these conditions, then you can have a nicely droplet separate, broken from the liquid jet. You can see this is an earlier breakup. Initially, when at the breaking point, the droplet may not be the spherical. Okay, but when you wait, maybe in the more several droplets more later, then the droplet since the strong surface tension of liquid, then this droplet will go back will retain their spherical shape. Okay, and later on from these pictures you can find out in the right hand side you will have a spherical droplet continuous move to the right hand side. Okay, this is the basic techniques we use for the single droplet burnings used in the presented in the literature. Okay. Now we go back to our original experimental observation. We find out we take the high-speed pictures. We use the high-speed camera to take droplet motions at different locations. The coordinate, the origin of coordinate is equal to 0 at the injection plans of your combustion, the index positions of your combustion chamber, or start to measure x equal to 0 here, and a continuous move to the downstreams and up to x equal to 10 meter. Then you can see this is the long combustion chamber we have. Okay. Now we take the pictures at x equal to 9 centimeter and also 15 centimeter and 20 centimeter. Okay, since the you cannot have a you have a large area to take a picture from the high-speed camera, then we need to have a pictures for one section, the other section, and another sections. Okay. Okay, we look at x equal to 9 centimeter. Actually, this is the in the near streams, in the more upstream sides near the flat frame. That means the droplets start to be ignited, and they will experience smaller. Okay, it's smaller droplet velocity because the droplet velocity is falling down by gravity. Okay, in this moment, actually, the droplet velocity is relatively small compared with the gas velocity, since we supply the gaseous mixture to support the flat frames, and those gaseous mixtures, hot products will continue to move from the upper part to the lower part. Originally, in the earlier regions, the gas velocity is higher than the droplet velocity. Okay, and by this way you can see there is the relative velocity exists for the droplet. You can see in these earlier regions, your friends actually there is an envelope frame. Okay, but since for a single droplet burning, they do not have an intense yellow color except in the wet frame regions. Then you can see the frame actually they surround the droplets and with the ball shape, and but the frame length in front of the droplet is longer, right? Actually, you can figure out because the Vg, the gas speed, higher than droplet speed. That means that you will have a relative velocity between droplet and the gas, and point to the downstream side, downward, and this relative velocity will push just like the flow stream as I described, acting on the burning of droplet, and push your friend to extend has a longer distance. In this case, is in the downstream side of your droplet. Okay. But you will find out when you move your camera to the middle region of your combustion chamber as x equal to 15 centimeter, you will see at this region, since we have influence coming from the gravity, the drop will be accelerate continuously. Initially, they may have a small velocity compared with the gas speeds, but later on, they will catch up the velocity of the gas flow. When they are very similar, if you do not have too much difference between gas speed and droplet speed, that means that they do not have a relative velocity acting on the droplet. Then the droplets will not be influenced by the flow convection, right? Then you can see the top one, actually they show is a more, the diffuse influence is more like a spherical frame, right? But later on, you will find out the frame change their position to the downstream of your droplets. Okay, originally is in the upstream side because the relative velocity is acting on acting into the acting on downward directions, right? And but now we start to have a droplet velocity larger than the gaseous velocity. Now the direction of relative velocity will point upward. Okay, then your diffusion will push further, has a longer distance in the downstream of your droplets. And you move your camera to the downstream further, you will see this is a typical Frank envelope, and you have a longer Frank length in the downstream of your droplets. Okay. This is a change from the up in the earlier region to the middle region and to the downstream region. You will find out initially droplets has the friends in front of the droplet, but later on the friend will be shrinked to become the spherical friend, and then later on when you go further to the downstream, then the friend will go to the back wall of your droplets. Okay. Yeah, this is I try to bring a lot of pictures together and I give you a sense to think about the motion of your droplets at different positions, and we use the so-called DAO field. Actually, this is provided by China Petroleum Company, and this is a typical field we will study. They come from the residues of the fuel production or petroleum productions. They have some impurity inside of the droplets. Okay, now we have the pictures for at different position from 4 centimeter up to 50 centimeter. Okay, then you can see in the beginning in the earlier regions, very close to the flat frame, and you can see frame exists in the front of the droplets. Okay, and gradually when the droplet reach to the 13 centimeters, actually the length of your diffusion frame in front of the droplets is continuously reduced. At this moment, they almost change their directions, the frame directions to the downstream of your droplets. And the frame length continuous increase if you move to the very downstream side of your combustion chamber. Okay, and finally, you will find out the frame actually in from the 40 to 45 centimeter, they have some side frame exist, and later on the frame will push to the wake regions of your flow. Okay, and you can see there is no frame surrounds by the droplet, surrounds on the droplets. Okay, and they can exist still have some burning in the downstream regions. And here you can see typically you can find out there is a slight ligament coming out, right? Yeah, this is what's happened actually. As I mentioned, DAO is so-called has some impurity inside of your liquids, and those impurity will be injected out in the burning process, and those impurity contains a certain amount of carbon can be burned. Then you can see there is some injection. Later on, I will tell you this is one kind of so-called micro explosion, and this is very important behavior for the application of multi-fuel, multi-liquid fuel. Okay, this is another one. The impurity was injected out, okay, in the burning process. And you can see there is a break image, right? Break image represents something injected out and cannot be burned out. As you remember, in the yellow flame regions, there's a lot of carbon particle exist. When they inject out from the high temperature environment, actually they will show their nature is a black color carbon particles. Okay. Therefore, when you go to the downstream side, you can have a more carbon exist in the downstream side. And this plot is very nicely to tell you the droplet originally has the diffusion flange in front of the droplet, and later on they will have some transition from the front side to the back side. And those kinds of variation depends on the balance of the gaseous velocities and also the droplet velocities. You should remember another influence coming the buoyancy effect. Okay, actually, when you have a spherical droplet with the spherical frame exists in a competitive flow, they tell you in this sense they still have a flow convections balanced with natural convection, which means the relative velocity will move to the downside a little bit. They still have a certain amount of radial velocity, and the loss flow convection will balance with the natural convection, since natural convection always exists in all the positions. Okay, but initially the downward flow convection is stronger than the natural convection. Then they push the frame in front of the droplet. Okay, but in the downstream region, actually the flow convection has the same direction with the natural convection. They have the same way to acting on the droplet. Then the frame the frame length will be increased as much as possible. You can see in the downstream side they have a longer frame length in the back of the droplets. And in the experiment, now this is very interesting. When you do the measurement for droplet diameters, that means that we measure the d square law, you find out they may have some fluctuation, but they still follow the d square law. The main thing is, actually, we mentioned the droplet evaporation has the same mechanism for the droplet itself. Okay, they experience the hot environment without combustion or with combustion. Actually, for the droplet, it's no difference. They just have a high temperature uh, uh, exists in their surrounding, right? Which means that the frame may disappear, but actually in the surrounding, the temperature is still high. Okay, since when you look at the real application, the spray combustion, actually for the whole combustion chamber, that contains the same, almost the same temperatures. Okay, somewhere maybe have a flame, somewhere do not have a flame, but all the temperature are reached to the very similar temperature distribution, high temperature. Then droplet itself still experience the same environment with or without flame. There is no difference, which means the droplet evaporation for droplet itself, actually they still follow the d square law. And additionally, I give you the a sequence for change the frame position from the in front of the droplet, then go back go to the back of the droplet. You can see we start from the initial condition. There is a small frame exists in front of the droplet, right? And the change, the shift to the downstream of the droplet. Okay, by these shiftings, they tell you this is a very nice pictures. We just focus on the change of frame positions from the upstream side to the downstream side of the droplet. And this is a sequence. They tell you you have the front frames, then you have a spherical frame, then they will oral frames, and then they will have side frame. Then later on they will separate from the original droplet and go to the later on they will go to the wake frame. This is a very nice pictures taken by the high-speed camera. And additionally, we can give you another experiment to introduce those kinds of frame structure, and I will emphasize it for the next video.